Okay, today we have Mike Shubrook
Shubrook, yeah.
from the university, doing a PhD in the University of Bristol, and he's also working with two people that you guys may know that are here. So please.
Sure. All right. Thank you. Yeah. Thanks for the invite, Leonie and Essen, for inviting me. So yeah, my name is Mike Shubrook. I'm a PhD student in the quantum engineering CDT at Bristol. But pretty much everything that I do PhD-wise is with Essen and Jake here in Manchester. But if you've never seen me before, it's because I work remotely. So I'm a little bit like all over the place, really. So yeah, this is work in collaboration with Essen and Jake, and we're looking at quantum heat statistics in the strong coupling regime. And the way that we look in this strong coupling regime is with this reaction coordinate mapping. So I'll explain everything, all these different terms in a moment. So a little bit of context. We're interested in open quantum systems. So we have a quantum system that's like surrounded or enveloped within a bath. And when this is the case, we can split up the Hamiltonian into a system, an interaction, and a bath term. And we'll sort of quantify the strength of our interaction term with some number, lambda. And usually in open systems, what we'll do is we'll try and find the equation of motion for the state of the system. And it's going to be made up of two parts. The first part is going to be basically asking, how does the system evolve when it's by itself? And the second part says, well, what does the bath do to the system? And then we have these two contributions, and it tells us how the state of the system evolves in time. And in order to derive an equation like this, which is called the master equation, we need to make two approximations, which are called the Born and the Markov approximations. It's not super necessary that we know what those are right now, but you just need to know that I need to make certain approximations about the system and its interaction with the bath in order to derive this master equation. And this particular master equation is what we call a weak coupling master equation, which basically means that it's dependent on the interaction term being small. So I use second order perturbation theory to derive this master equation, which means that it's only really going to give me a good answer up to second order in the coupling strength, lambda. But we're actually interested in quantum thermodynamics, so we're not necessarily interested in the state of the system. We want to ask questions like, how much work can we extract from the system, or how much heat does the system exchange with the bath? And specifically, we're interested in these questions in the strong coupling regime, so where this lambda number is going to be bigger than 1. And then what happens in this regime is the boundary between the system and the bath sort of becomes blurry. So you can't point and say that's definitely the system and that's definitely the bath. The distinction between them becomes a little bit ambiguous. And then also, when the coupling strength is large, that master equation that I just showed you is going to break down. So the specific open system model we look at is called the independent boson model. And if anyone's heard of the spin boson model, it's that basically, but with no tunneling term. And the reason we look at this is because it has analytically solvable dynamics, which means that I can get the reduced state of the system, the equation of motion for the reduced state of system exactly. And the reason that that's good is because eventually I'm going to derive a new master equation, and then I can compare my master equation with these analytical dynamics. And I'll be able to say, okay, my new master equation works. And also, this is a time-independent Hamiltonian, which means that there's no work contribution. So there's no work being transferred to or extracted from my system here. Yeah?
So sigma that represents the system, right?
Yeah, sorry, so I'll explain these terms now. So I just have a two-level system that has some energy split in epsilon, and it's coupled to a bath of harmonic oscillators that has this Hamiltonian here. So just a two-level system surrounded by a bunch of quantum harmonic oscillators. Is that okay? Yeah?
Thank you.
Nice. Okay, so what is heat statistics all about? So if we're thinking about measuring heat, we might think maybe there just exists some Hermitian observable that I can measure with respect to a quantum state, like we're used to with pretty much every other measurement. And then I'll get one of the eigenvalues as the outcome, say like here. So I measure it with respect to a quantum state, and I get a particular eigenvalue with some probability. And then maybe I can take the expectation value of this operator, and I'll get like the average amount of heat or something like that. But it turns out that heat's not an observable, and that's because it's not a state function. So only state functions have Hermitian observables associated with them. So for example, internal energy, that's a state function, and it has the Hamiltonian. Position is a state function, momentum is a state function, and these have Hermitian observables associated with them. But path functions don't have Hermitian observables associated with them. And we're interested in heat statistics here, and heat statistics is a path function, which means that there is no observable that I can measure with respect to a quantum state to get the amount of heat in my system. So now the question is, well, how are you going to define heat? And let's think about what heat is. Like maybe we can describe it as some sort of disordered energy. We can use a sort of like reverse definition and say, well, heat is not work, right? They're sort of like opposite in a strange way. So if we can define work, then maybe we can say that heat is like the opposite of that kind of. And then in the literature, people define heat as changes in the energy of the bath. But I said before, we're going to look in the strong coupling regime, where the definition of bath becomes ambiguous. So this definition isn't super helpful here, because what do you mean by bath? And one way that we can define heat is using this thing called the two-point measurement protocol, which is what we focus on in this work. And before I get onto that, there's going to be a slightly annoying change in notation. So rather than a system inside a bath, I'm going to draw my system connected to the bath like this. So this line here basically just represents the fact that they interact. And then the black box surrounding everything means that I assume that the system and the bath are a closed quantum system. So they evolve unitarily altogether. And the reason it's called FB instead of just B for bath is I'm going to refer to it as the full bath, which will make sense shortly. So everything inside this box is just this quantum system coupled to a bath of harmonic oscillators. So my bath is just a bunch of harmonic oscillators. And this is the two-point measurement protocol. So this is how we define heat. So first of all, what I'm going to do is I'm going to take my system and just prepare it in some initial state. And then what I'm going to do is I'm going to assume that I can perform a projective measurement onto the Hamiltonian of this bath. And if I do that, I'll get one of the outcomes, right? I'll get, let's say, M0. That's one of the eigenvalues of this Hamiltonian. Then I'll let everything inside this black box evolve unitarily, because it's a closed quantum system. And then I'll perform another one of these projective measurements onto the bath Hamiltonian. And maybe I'll get a different, or maybe I'll get the same eigenvalue. It doesn't matter, I'll get one of them randomly, and I'll call that MT. And then what I do is I define heat as the difference between these two measurement outcomes. And because these measurement outcomes are going to be random, this definition of heat is stochastic. So I need to repeat this a bunch of times and build a probability distribution. So the probability distribution is what I want, but it's actually much easier to work with its Fourier transform, which is called the characteristic function. Right, so this is what I want. I want the probability of transferring a certain amount of heat in a certain amount of time. But what I'm actually going to work with is its characteristic function. And we'll see why in a minute. And the characteristic function is dependent on this thing called the counting parameter or the counting field. And it's basically just the conjugate variable of heat. So heat and this counting parameter chi are related in the same way that like position and momentum are related, or frequency and time. Just conjugate parameters of each other. So maybe this might be a bit helpful. So imagine I've got some signal and I'm going to Fourier transform it. And what am I going to get? I'm going to get like a bunch of delta functions. So the thing on the left is going to be what my characteristic function might look like. And the thing on the right is going to be my probability distribution. So if I draw a little set of axes, it might make a bit more sense. So there's going to be peaks telling me how much probability there is of transferring a certain amount of heat between my system and bath. So the characteristic function can be written like this, and it doesn't matter what this looks like really, but I can show you the different parts of the two-point measurement protocol. So here's preparing my initial state. This term comes from my first measurement. Here's my unitary evolution, and then this part comes from my second measurement. But the details don't matter. What matters really is that I can rewrite this using the cyclic property of the trace as the trace of a generalized density operator for the system and the bath. So this density operator is transformed in some way by this parameter chi. And it's going to mean that the trace is no longer equal to 1. So it's not a true density operator, it's this generalized density operator. And so what does this mean? It means that I have my characteristic function and it's equal to the trace of this density operator. So if I can somehow find out what this density operator is, then I can just take the trace and I get my characteristic function, which I inverse Fourier transform to get the probability distribution that I want. So if I was able to find an equation of motion for that state and then solve it, then I would get what I want. Right? I would get a list of the states as a function of time. I would take the trace, get my characteristic function, inverse Fourier transform, and get the probability distribution that I want. But this density operator is for the system and the bath. So it lives inside a huge Hilbert space. So it's pretty much impossible to track the state of it. To track its motion as a function of time. So what I can do is I just split the trace into a trace over the system and a trace over the bath. And then I call the trace over the bath of this state the reduced state of the system. And now what I just need to do is, if I can find an equation of motion for this thing, so similar to the master equation that I showed you at the start, except now it's going to be slightly different because it's in this chi-dependent frame. So if I can derive an equation of motion for this thing, I just take the trace of it and I get the characteristic function that I want. So this work basically revolves around deriving an equation of motion for this state, choosing some appropriate initial condition, and then solving the equation of motion. Then I get my characteristic function. And the characteristic function contains all the statistics of the transfer of heat between the system and the bath. So the full counter statistics is called. So like I said, this equation of motion is going to be a master equation, right? And I said that I need to be able to make the Born and Markov approximations. And I can't always do that, especially in the strong coupling regime. Because like I said right at the start, in the strong coupling regime, I can't perturb about my coupling strength because it's too big. I need to be able to perturb about a small parameter. And what I can do is resolve the identity with a unitary and its conjugate, and just insert it inside the trace. So what am I doing there? I'm basically just taking a number and multiplying it by 1. So I'm leaving everything the same. And then what I can do is use the cyclic property of the trace again, and I'll end up with, say, like V rho, V dagger. And what does that do? It changes the basis that I'm looking at my state in. And if I choose a unitary that allows me to rotate into a frame where this interaction between the system and the bath looks small, then I can derive an equation of motion in that frame. So, all good? Yeah?
You do this transformation for the whole system, bath plus the system.
Yeah, so it's done for the full system and the bath, and then we do this thing where we break up the trace into a trace over the system and the trace over the bath.
Right.
Okay?
And it doesn't mix the states.
Pardon?
It doesn't mix states of the bath and the...
Does it mix states of the bath and the system?
Yes.
It depends on the transformation that you do, yeah.
Alright.
Yeah. So the way I think about it is, like, we have a vector that represents our state, and then we're basically just changing our view of that vector, and we're able to like extract different amounts of different parts of information about the vector depending on where we're looking at it from. So the unitary just sort of rotates our view of the vector, and depending on the particular situation, I might want to look at it in different directions. So I need to basically choose a unitary that's going to let me look in the strong coupling regime. That's basically what I'm trying to do. I'm trying to figure out which V will let me make this distinction here, going from trace over the full system and bath state to just a trace over the system state. And the particular unitary that I'm going to choose is one that performs this reaction coordinate mapping, which I'll explain now. So this is a unitary mapping, so no approximations, that acts on the Hilbert space of the bath, leaves the system alone. And essentially what it's going to do is redefine the boundary between what I call system and what I call bath. So I start off with my system strongly interacting with an infinite number of modes in the bath. So it's strongly interacting with a bunch of quantum harmonic oscillators. Right, so there's a bunch of harmonic oscillators in this bath. Now, if we have a situation where the system isn't actually interacting with all the modes, but maybe it only interacts with a few of them, then this is where I'm going to use the reaction coordinate mapping. And essentially what it does is it takes these modes that the system is interacting with, and it sort of pushes them all together into one mode, which I call the reaction coordinate. And this reaction coordinate, because it's a boson and it's surrounded by a bunch of bosons, just weakly interacts with the rest of these bosons. So now what I can do is I can just take this reaction coordinate out. So now I've got a system strongly interacting with this reaction coordinate, which is just one boson. And this one boson is weakly interacting with all these other bosons in the bath. So I'll just make the reaction coordinate the same size to make it look nicer. And I'll change the colour of the bath just to let you know that I've taken something out of the bath, right? So it's not the same as it was before. And I'll call this thing the residual bath, right? It's residual because I've taken something out of it. So I started off with the full bath, I took the reaction coordinate out of it, and I'm left with the residual bath. And this still has an infinite number of modes in it, right? Because infinity minus 1 is still going to be infinity. So this is what I started with, a system strongly interacting with the full bath. And I've mapped it exactly to the system strongly interacting with this single mode, the reaction coordinate, which is weakly interacting with an infinite set of modes in this residual bath. So everything inside that dotted box is the same. So the full bath is made up of the reaction coordinate interacting with the residual bath. And now what I can just do is I'll just draw a box around these two things instead, the system and the reaction coordinate, and I'll call this an extended system. So I've gone from a system strongly interacting with an infinite number of modes to an extended system weakly interacting with an infinite number of modes. So in this first case, because this interaction is strong, I can't perform any perturbation theory to derive a master equation for this thing here. But after the mapping, because this interaction is weak, I can perform perturbation theory in order to derive a master equation for this thing. So this is basically what we're going to do. We're going to derive a master equation for this extended system, which is made up of a two-level system and a boson. So it's going to be a little bit more computationally expensive because I'm simulating a larger Hilbert space, but it's going to let me look in the strong coupling regime, which is nice. So this is the spectral density of these two baths, or the interaction between the system and the full bath here, or the extended system and the residual bath here. And essentially what we need to look at is the strength, right? So we've got 1.5 up here, so pretty strongly coupled. But we see that the residual bath is really, really weakly coupled to the extended system, which means that I can derive an equation of motion, a master equation for this extended system. Okay, so now we go back to the questions that we were asking at the start. How are we going to define heat? So first of all, the reaction coordinate does a couple of things. It lets us ask this question, which bath are you talking about when you say changes in the energy of the bath at heat? So is it changes in the energy of the full bath? Oops. Or is it changes in the energy of the residual bath? And then we also said that heat is not work, right? And then there's a question of, is it possible to extract work from the reaction coordinate? If it is, it might not make sense to define heat as changes in the full bath, because the full bath sort of contains this reaction coordinate. So maybe there's going to be some work here that we could extract. Whereas here, we've moved the reaction coordinate into this extended system. So it might make more sense to define heat as changes in the residual bath Hamiltonian, because there's nothing in this that we can extract any work from. So we put together the two parts that I've talked about. So I'm going to put together the 2-point measurement protocol and the reaction coordinate mapping. And essentially the only difference is going to be, what Hamiltonian do I perform these projective measurements on? So I can perform the projective measurements on the full bath Hamiltonian, here and here, and I end up with some probability distribution. Or I can just perform the projective measurements onto the residual bath Hamiltonian, and I'll end up with some different probability distribution. So these are two ways of defining heat: changes in the full bath Hamiltonian or changes in the residual bath Hamiltonian. So this is what we had at the start. The characteristic function is equal to the trace of this density operator for the system and the bath in this chi-dependent frame. And now I just choose a unitary which performs this reaction coordinate mapping, and it lets me rewrite this as the trace over the extended system state in this chi-dependent frame. And now I derive an equation of motion for this thing. So we call this the counting field dependent reaction coordinate master equation. And then what do I need to do in order to find this characteristic function? I just need to choose some initial condition and solve the master equation. So you might be thinking, how are you going to test these two different definitions of heat? it looks like everything is going to be the same. And it basically all just comes into choosing an appropriate initial condition. So depending on which initial condition I choose, I either count changes in the full bath Hamiltonian or I count changes in the residual bath Hamiltonian, but the master equation is the same. And first of all, what we need to do is make sure that our master equation actually works, and this is where the independent boson model dynamics come into it. So this is why we're using the independent boson model, because it has analytically solvable dynamics, which means that I can test that my master equation works. Okay, so 3 main things that I'm going to show you, different characteristic functions. 2 of them count changes in the full bath Hamiltonian. Right? One of them uses the exact independent boson model dynamics, and the other one uses our reaction coordinate master equation. So basically, if the black and blue lines agree with each other, it means that our master equation does what we want it to do. If that's the case, then we should also be able to use the reaction coordinate master equation to count changes in the residual bath Hamiltonian. And that lets us then test our 2 possible definitions of heat, both using the same method. And the reason why we have to do this is because there's no way to exactly count changes in the residual bath Hamiltonian. So that's where this 3-step process comes in. I check my master equation works. I then assume that if it works for the full bath, it has to work for the residual bath. And then I use that assumption to then test my 2 different definitions of heat. So here's the real and imaginary parts of the characteristic function as a function of the counting field or counting parameter. So there's 2 things we need to ask, right? Do the black and blue lines agree? If they do, then the master equation's doing what it should do. And then after that, we say, well, what's the difference between the blue and red? Because those are our 2 different definitions of heat. Now we can see that there's a pretty decent agreement between the black and blue in the region of small chi. So between about -50 and 50, it's pretty good agreement, and then after that, things start to drop off. And that's because we've made certain approximations to do with the product of chi and the coupling strength, but that's not super relevant, because what we can just do is zoom in at around chi is 0, and then we see that the agreement is very good. So the black and blue lines pretty much overlap with each other. So that means that in this region, the master equation is working really well. And you might think, well, you've just zoomed in on where your work looks good, and that is kind of true, but there's a property of the characteristic function, which is that all moments of the probability distribution associated with it can be calculated by taking derivatives of the characteristic function at chi is 0. So if your characteristic function is good at chi is 0, then you can sort of just get all the moments of the probability distribution anywhere. Which we have, right? We have good agreement between the exact result and our reaction coordinate master equation result, close to chi is 0, so that's nice. And then we say, well, what's the difference between the red and blue lines? What's the difference between our 2 different definitions of heat? And we can see that they're different, right? But nobody can perform inverse Fourier transforms in their head, so it's pretty hard to see what this actually looks like. So what we'll do now is we'll look at the mean of the probability distributions associated with these characteristic functions as a function of time. And here we can see that there's quite clear differences between our definition, at least in the mean. So again, the black and blue lines agree, that just means our master equation tracks what it should do. But the main thing we want to look at is the difference between our blue and our red curves. And we can see that they're very, very different, right? So the blue is asking, on average, what's the change in the full bath Hamiltonian? And we can see that it oscillates there's quite pronounced oscillations. And the red is asking, on average, what's the change in the residual bath Hamiltonian? And we see that it just sort of slightly oscillates and increases towards this steady state value, which is shown by the dotted line here. So these results show us that these 2 different definitions of heat are quite different. And then we look at the fluctuation dissipation relation. So we're just taking the ratio of the fluctuations, so the variance to the mean in the steady state, and essentially all we really need to show here is that they're approaching the fluctuation dissipation relation limit of 2 here, which is nice to see. So, I think this is sort of like a quantum version of the first law, where we relate a change in energy to a work contribution and a dissipative energy change. So this term would be if we had some sort of external drive, which we don't, so we'll just ignore that term. And this term is due to a system's interaction with the bath. And this can actually be broken up into a change in heat and a change in what's called ergotropy. So ergotropy is how much work can you unitarily extract from a system. So usually when we think of the first law, we think it's broken down into work and heat, but that's only the case if the change in ergotropy is 0. And essentially what this is telling us here is that an interaction with a bath can actually transfer ordered energy to the system. So here we look at the ergotropy. So before, we were looking at changes in the bath, right? We were looking at the changes in the full bath, and we were looking at changes in the residual bath. Now, we're asking, how much work can I unitarily extract from the system, and how much work can I unitarily extract from the extended system? And they're shown by these orange and green lines, respectively. And we can see again that they're very different. But importantly, what we see is that there's a pretty significant increase in the amount of extractable work in the extended system compared to the system. And what does that mean? Well, it means that we can extract more work if we have access to this reaction coordinate, which was originally part of the bath, but now we've redefined it as part of our extended system. Now, there's obviously an issue in asking, well, how are you going to unitarily extract that work? And I have no idea, to be honest, but it's just quite nice to see that we can, in principle we can. So this is mainly what we've been looking at. We've been looking at dissipative energy changes between a system and a bath, broken up into heat and a change in ergotropy. And we've shown that there's pretty significant differences between heat, if we define it as changes in the full bath, given by this blue curve here, or changes in the residual bath, given by this red curve here. And then we've also shown pretty significant differences between the change in ergotropy for the system and the extended system, which we see in these curves here. So, conclusions. Our reaction coordinate master equation captures thermodynamic properties of the bath, right? The black and the blue lines look the same. That's basically what I'm saying. Our two different definitions of heat, being changes in the full bath and changes in the residual bath, give pretty significant differences in their mean. And we can also extract more work from this extended system than we can from this system here. So that's pretty much it. I'd like to thanks everyone for listening, and thanks to Essen and Jake for all the help. If anyone's interested, I have some videos online where I sort of go through some more technical details of this. And if anyone's got any questions, feel free to ask. So, thank you. Yeah?
Is it always possible to extract this reactive boson coordinate, right? What's it called?
Reaction coordinate.
Yeah, reaction coordinate.
Yeah, so I think essentially what you want is a spectral density that is peaked like this. So the more sharply peaked it is, then the better off you are using this mapping. Because essentially what the mapping is doing is it's saying, I'll just approximate this peak as a delta function.
Oh, okay.
Yeah. So the more broad your spectral density is, the worse off the mapping will be.
But this is spectral density for what? For the bath? Or
Yeah, for the bath, yeah. So this top one is for this bath, and this bottom one is for this bath here.
Okay, but this means that there is a sharp excitation, right? There are sharp excitations in the bath, right? At a certain energy. Yeah, if there's
at the energy of this thing, which we call the reaction coordinate.
Particle somewhere in the spectrum, right? Is that what it? Am I understanding this correct?
I think so. I think what you're just describing is what we call the reaction coordinate.
Yeah, but what if the spectrum is like I don't know, it's more spread?
Yeah, then this isn't a good technique to use.
Okay, and this is okay, fine.
Yeah.
Okay, so it's not all.
Yeah,
That's it's not completely true that it doesn't work
Okay.
for broader spectral densities, but you just have to be careful about you have to be more careful about the parameter regimes. The perturbation might not be as small to the residual, but
Okay.
you could always iterate the mapping as well if you wanted. Sorry.
Okay.
Yeah,
Thank you.
so this is a very kind of coherent bath, meaning that it's not really like a, I don't know, thermally distributed something or.
Well,
I don't know what you mean.
Yeah, it starts in a thermal state. It's more like a lossy cavity or something like that. But yeah, I would say it's not just limited to these situations, but these are nice situations to benchmark against.
I have another question. Can you explain one more time the point of the 2-point protocol? Why is it 2-point and how does it work? Why not 3-point protocol?
Yeah, that's a good question. So I don't know, maybe just 2 because that's the easiest way that I can get a difference. I don't see why we would measure it 3 times.
So you take a measurement, then you unitarily evolve your system, and then you take another measurement.
Yes. So we define heat as changes in the energy of the bath. So if I want to change, I just need 2 values.
Okay, and for how long do you evolve it? You evolve it unitarily.
So that's just whatever time I want to extract
Okay.
my probability distribution from.
Okay.
Yeah.
Okay, this makes sense.
So sort of like a free parameter that I can just change.
Thank you.
Yeah.
Any other question?
I was interested in the fluctuation dissipation. Well, so it seems like even though the mean is very different, the ratio of the fluctuations to the mean is the same in both cases.
Yeah, so I haven't got the variance on here, but the variance plot pretty much looks exactly the same as the mean. Obviously, like the values on the y-axis are different, but like the oscillations are the same.
So it's sort of interesting, isn't it? Because if you go back to your like you would expect everything to agree at high temperature where you're reaching like the semi-classical limit. You wouldn't necessarily expect it to agree as you go down to low temperatures because you get deviations from the classical limit there due to quantum effects. But it seems like regardless here you're getting the same deviation.
Yeah.
What's the dashed line?
So that is like the fluctuation dissipation relation, like limit. It approaches 2.
The classical limit, right? Semi-classical limit.
Why do you expect that to hold?
So I think it's because there's no. So it comes from using the like Jarzynski inequality, and then from that you can get the work fluctuation dissipation relation. Because it's the independent boson model without any time dependence, we can just say that like work is the same as heat, and the free energy change is 0. So it basically just becomes the same thing for heat.
Okay, I get what you mean.
Yeah, you've used the independent boson just as like your testing, your exact model to compare to. So is there an intention to use this for non-independent boson?
Yeah, so we can use it for the spin boson model.
Okay.
But like all the results, we've just got this exact result on everything just to make sure that it all agrees. But yeah, we can just use this for the spin boson model as well.
Does that have any impact on the reaction coordinate?
No, so the reaction coordinate only acts on the Hilbert space of the bath. So we can change the system. I mean, I think we can probably just change the system to anything we want. It doesn't need to be a spin, and it would still work.
Okay.
But obviously, then the master equation would change, but the reaction coordinate mapping would stay the same.
Yeah. Would changing your coupling operator change the effectiveness of the method, I think, at all?
I don't think so.
Okay, so if there are any other questions, let's thank Mike again.
Sweet, thank you.